production. Just to check, so thanks a lot for inviting me. So I'm going to present this new work, which is about contextual bandits with concave rewards applied to fair ranking. So it's a paper that we just published on Archive and is currently under review. And this is joint work with my colleagues from Meta AI, Elvis de Matob, Matteo Pirota, Alessandro Lazari, and Nicolas Usunier. So a bit about myself. As Haolun said, I'm a PhD student and I'm in my final year. I'm based at Université Paris-Dauphine and I'm part of a joint program with Meta AI since 2020. And my research topic overall is about fairness in recommender systems, mostly using concepts from normative economics. And I'm advised by Nicolas Usunier from Meta AI and Jamal Latif and Long. And so I'll first give a bit of very briefly present what my PhD is about, and then I will switch to the actual paper. So I'm broadly interested, as probably some of you, in the societal impacts of modern recommender systems, and in particular, issues related to bias, discrimination, and fairness in recommender systems, which attracted a lot of attention from journalists as well as auditors in academia. So there has been a lot of interest in this topic in recent years. And this is very important to consider the impacts of modern recommender systems because they allocate economic opportunities to many of the stakeholders. So that includes their users, because recommender systems are able to recommend job postings, housing ads, goods and services for sale. But they also impact the item side by allocating exposure to an audience, which may directly translate in income for content creators, businesses, newspapers, advertisers. And so by allocating exposure, recommender systems mediate between the interests of the users and also the item producers. And so it's important to make sure that this allocation is fair to both users and item producers. And so this is a topic that gained a lot of interest in recent years from the research community. And so the general approach that I take this PhD is to acknowledge fairness has been studied for decades in welfare economics and social choice to address problems such as fair resource allocation, inequality measurement, voting, and many other problems. And so the approach is to ask, how can concepts from this literature help us design fairer recommender systems? And what are the algorithmic challenges involved when using those concepts to design new algorithms? And so the focus of this work that I'm going to present today is more on the algorithmic part. It's about presenting a new algorithm for fairness in rankings that has in the background these economic notions. So this is the topic of the paper I'm going to present now. So the outline of the paper is the following. So first, I will talk about contextual bandits for personalized recommendation. And then I will present the setting that we study, which is contextual bandits with concave rewards. And then I will present how this framework and our solution applies to the problem of fairness in rankings. So personalized recommender systems are everywhere, and they help us recommend music, bakeries in Paris, or content on Instagram. And so key feature of these recommender systems is to be able to generate personalized recommendations by learning from user feedback. And so a popular paradigm for personalized recommendation is contextual bandits, which I'm going to present now. So contextual bandits are a sequential decision-making framework where an agent interacts with their environment, which is represented by a current user. And so at each time step, the agent observes a context vector, xt, which represents the features of the current user. and takes an action 80, which can represent a single item or a more structured action, such as a set or ranking of items. And so the agent presents that action to the user. And then the user sends a signal to the agent, which is the reward RT, which can represent a click, a like, or another engagement signal. And so the traditional objective is to maximize the cumulative reward collected by the bandit agent. And so in contextual bandits, the main aspect is that the expected reward function mu is unknown and must be learned online. And the agent only observes a noisy reward realization for the action that the agent takes. And so I'm going to give an example of a standard contextual bandit algorithm that addresses this personalized recommendation task. So LinUCB is an algorithm that assumes that the reward is a linear function of context X. And so the optimal policy would be to take the action that maximizes the reward at the current context. But of course, the algorithm doesn't know mu. And so what LinUCB does is that it estimates the expected reward function mu by regression based on their history. And then the algorithm derives an upper confidence bound on the expected reward mu and plays the action that maximizes this upper confidence bound. So that's how LinUCB works. And so I just wanted to present it here because I will get back to this algorithm later in this presentation. And so LinUCB and other contextual bandits typically optimize for a single reward. And so the thing is that optimizing a single reward is not enough anymore in modern recommender systems. This is because, for example, there are multiple, many possible recommendation metrics. So we could measure user engagement by clicks, streaming time, or likes, but there are also other objectives such as advertising revenue, for example. And also, recommender systems need to account for the interests of multiple stakeholders. So there are the users, the content produced, but also the interests of the platform. And so this is something that people have started to push for in recommender systems. And importantly, and this is like my main topic of interest, recommender systems also impact the item side. Because behind the items that are being recommended, there are people who can be creators, advertisers, job candidates, people who work for newspapers. And so the goal of fairness of exposure and all the work that's been done in this literature is to make sure that the recommended system is also fair towards item producers. And so this is why optimizing for a single reward measuring user satisfaction is no longer enough. And so this is why, this is what motivates the study of our setting of contextual bandits with concave rewards, which I'm going to present now. So in contextual bandits with concave rewards, instead of receiving one single scalar reward at each time step, the agent receives a vector of multiple rewards. For which the expectation is also unknown and is also represented by a vector of size d. And so the goal of the contextual bandit agent in the concave reward setting is no longer to maximize a cumulative scalar reward, but rather to maximize a concave function which defines a trade-off between the d rewards. So this is the new objective, and this is what we call contextual bandits with concave rewards. I'm going to give a few examples of how we can instantiate this problem. So first, let's get back to the problem of optimizing multiple recommendation metrics. So this is a problem that has been studied by researchers at Spotify for optimizing multiple metrics in music recommendation. And so in their setting, there are D recommendation metrics, and the bandit agent receives a vector of rewards at each time step, where each entry of the vector represents a different metric. So we can have, for example, one entry which is the binary click, another entry which measures the streaming time, and another entry which measures the generated revenue. So it's a convenient way to model this multi-objective problem. And so the trade-off between metrics is defined by an aggregation function f, which can be weighted average of these objectives, or an ordered weighted average of these different metrics. So this is the problem that was studied in this paper. We can also model the problem of fairness of exposure in rankings using this framework of concave rewards. So here we consider a recommendation task with m items to rank. And so the traditional objective and recommendation would be to maximize for a proxy of user satisfaction measured by a single scalar reward, RT. But when we want to account for fairness of exposure, we want to take into account both this proxy of user satisfaction, but also the exposures of the items. And so we model this by a vector of m+1 rewards, where m is the number of items. And so here, the first m entries of the reward vector correspond to the exposure of each item. And the last entry corresponds to a measure of user satisfaction. And so in the fairness literature, there has been several formulations for fairness, but we could consider a fairness-aware objective, which would be a trade-off between user satisfaction, which is like the last entry of the reward vector, and a fairness measure that takes as input the items exposures. I'm going to give a few examples here of fairness objectives. So for example, these fairness objectives could be formulated as trade-offs between average user satisfaction and a measure of item fairness. For example, measuring item fairness with item inequality with the standard deviation, which gives a smooth objective. And another possibility, which is found perhaps in more work because it's a well-known, it's a better-known inequality measure. Another possibility is to measure inequality by the Gini index. And so this gives an objective that is non-differentiable, but we can also address that in our framework. So most of my work, apart from this one, has been focused on designing concave fairness objectives. I'm going to do a shameless plugin here to talk about, just to mention that I worked a lot about those Gini indices. But like in these works, I talk more about the framework and not the algorithm, whereas here I'm more focused on the algorithm. And so getting back to the contextual bandit with concave reward problem, which addresses these examples. So the objective of the algorithm in this theoretical problem is to minimize the regret of CBCR. CBCR is the abbreviation of the problem. And so the benchmark here is with respect to an optimal stationary policy, which is a mapping from context to distributions over actions. And the measure of performance for the algorithm is the trade-off between the cumulative rewards collected by the algorithm. And so since the expected vector of rewards mu is unknown to the algorithm, it must learn to maximize this quantity in an online manner. There has been a very little previous work on the contextual setting in Bandits with concave rewards. And so previous work was limited to finding an optimal policy within a restricted finite set. And so in these works, it was possible to find an optimal policy by directly searching in this small policy space. In our work, we make no assumption or restriction on the policy space. And so this means that we cannot do direct optimization because the policy space can be arbitrarily large, as would be the case in recommendation. And so what we do in this work is to propose a solution based on a reduction, which removes any need for direct optimization in policy space. So this is like more the technical part. So I will now present the reduction to scalar reward bandits. So the way our solution works is that we start from a general complex theoretical contextual bandits with concave rewards problem. And then we show a reduction to a problem of contextual bandits in the usual scalar reward setting. And so what we show is that we can use any contextual bandit algorithm, so that can be linear CB, Thomson sampling, whatever, to solve the problem of concave rewards. So the way that the reduction works is that we start from a CBCR problem, and we define the associated scalar reward contextual bandit problem, where the context is simply an augmented version of the context of the problem, where we plug the gradient of the function in the context. And we also define scalar rewards by doing some sort of adaptive weighting of the original vectorial rewards with the gradient. So this may sound a bit mysterious, but the main message here is that we associate to the CBCR problem usual contextual bandit problem, which has a scalar regret that we can define. And so the main result of the reduction is that the regret of the original CBCR problem is bounded by the regret of the associated scalar reward bandit problem, plus a vanishing term. And so the conclusion is that thanks to our reduction, we can turn any contextual bandit algorithm into an algorithm for CBCR. So really, we can use linear CB or other variants of contextual bandits to transfer them into an algorithm for CBCR. I will give like a rough overview of how the proof works, but the ideas behind that is that we rewrite CBCR as a constrained convex optimization problem in the space of feasible rewards. And so there are various ways to address this kind of constrained convex optimization problem. And so one algorithm for that is the Frank-Wolf algorithm in convex optimization. And so Frank-Wolf works by taking at each time step a step in the direction that maximizes a linearization of the problem. And so what we prove in the paper is that each step taken by Frank-Wolf actually looks a lot like a scalar reward contextual bandit problem, where the goal the goal of the bandit is to take the action that maximizes this quantity, which is actually a scalar. So that gives us a scalar bandit problem. And so, yes. And so the question is how to relate these two quantities, like how are these related? How is Frank-Wolf related to contextual bandit? And so the way we prove that, so we use standard arguments from convex optimization proofs. And so we are able to bound the regret of CBCR. And so what we show is that this leads to a term which is bounded by a vanishing term by linking these two quantities, plus the regret of the scalar bandit. So that's roughly how it works. And so the main conclusion is that we can use this scalar reward bandit algorithm to address CBCR. So that's the math behind it. And so this, thanks to this reduction, we can use it to implement algorithms for CBCR. So I'm going to present here one of our algorithms, which is called FW-CB. And so here is a simple setting where actions are single items, so not combinatorial. And so how the algorithm FW-CB works is that we can just use linear CB off the shelf and give to linear CB the history of past contexts, actions, and rewards of the associated scalar bandit problem. And so that's exactly how we define FW linear CB. And FW in linear CB is an algorithm for concave reward setting. And so we directly obtain for free a regret guarantee of this CBCR algorithm, which is simply bounded by the regret of linear CB. And the regret of linear CB is well known because it's a very well-known paper in contextual bandits. So this is how we can just use linear CB to solve contextual bandits with concave rewards under certain assumptions. The question is, okay, so here the assumption is that the arms are just single items. And so how can we translate that to the fair ranking setting? And so this is what I'm going to present now. Oh, and just like this setting with where we just use linear CB, can actually be directly applied to the first example, which consists in optimizing multiple recommendation metrics. So now I'm going to present how to apply this work to fairness in rankings. So fairness in rankings. So I'm going to present first the ranking problem. So the setting is that we have m items to rank. And we at each time step, the bandit agent observes xt, which represent the features of the current user. And then there is, for the current user, x with feature xt, the value of item j is measured by a value vj. And it is unknown to the recommendation agent. And actions here are rankings, which are represented as permutation matrices. And the observation model is the following. So for each item j, the agent observes if the item is exposed or not, and if the item is light. So this is like a setting that, for example, reflects applications like news feeds on mobile apps, where the system is able to know whether the item is observed by the user, and also if the item is liked. So you have like this double feedback. And so in the fair ranking problem, as I said earlier, there is not one objective, but m+1 objectives, where m is the number of items. And so what the algorithm observes is a vector of g equals m+1 rewards, where the first m rewards corresponds to the exposures of each item. And the last entry of the reward vector is the satisfaction of the current user measured in number of likes or other or clicks. And so what the algorithm doesn't observe is the expected rewards, which here are given in the position-based model in ranking. So the expected exposure of the item j only depends on its rank, and the probability of like or click only depends on the rank and the value of the item j for the current user, which has context x. So these expected rewards are unobserved, and the agent only has access to the vector of realized rewards. And so earlier I gave example of fairness objectives, which would be a trade-off between a measure of user satisfaction and a measure of inequality of items exposures. And so I'm going to present our algorithm for this task, which is called FDAB linear CB rank. So FDAB stands for Frank Wolf, which underlies the proof of our reduction. And so we start from an existing contextual bandit algorithm for ranking without fairness. And so the way that this linear CB rank algorithm works is that it computes an upper bound on the value of each item for the user, and then it plays a ranking that sorts items by estimated value for the user. When we apply our reduction to this using this linear CB rank algorithm, we obtain an algorithm for the fair ranking CBCR problem, which is called FDAB linear CB rank. And so the way it works is that it also computes an upper bound on the value of the item for each user, but it plays the ranking that sorts items by estimated value for the user plus an item boost. So that's how the algorithm works. It doesn't just like rank items by estimated value for the user, as linear CB rank would do, but it also adds a boost, which is based on the gradient of the function. So what that means in practice is that we have an adaptive boosting, which boosts items that had low exposure in the past. So this is the result of the reduction, but it also have an intuitive interpretation, which means that at each time step, we boost items that have received low exposure in the past. And this low exposure is measured by the gradient of the objective. And so this gives us the first algorithm for fair ranking with contextual bandits, which has theoretical guarantees. So there are algorithms that do contextual bandits with fairness, but doesn't apply to ranking. There are other algorithms that apply to this setting, but don't have any theoretical guarantees. So we believe it's a nice contribution to this problem. And so we conducted experiments on the music recommendation task. And so we used data from Last.fm. And so here, what we plot is the value of the objective, where the objective is a trade-off between average user satisfaction and a Gini index of the item's exposure. And so we compare our algorithm to a baseline in red, which is a heuristic for ranking bandits for fairness that doesn't have theoretical guarantees. And so what we show is that these guarantees are not for nothing, because in practice, our algorithm converges to the highest value. And so even if the red baseline performs well for the first iterations, at some point, its performance starts to decrease. And so that's how we observe that the algorithm that we propose has interesting dynamics, because it reaches the highest value at convergence. And then we observe what happens after a large number of iterations by representing the trade-off between user satisfaction and item inequality at convergence. And so what we observe is that our algorithm obtains good trade-offs between total user utility and item inequality. And this is at all levels of inequality. Whereas a baseline that applies a hard fairness constraint leads to a strong decrease in user utility. And so this is how another illustration of the usefulness of the algorithm, because at convergence, it provides high user satisfaction while still reducing inequality between items. And so the conclusion of this work is that we provide the first algorithm for the theoretical bandits with Concave rewards problem that has provably vanishing regret. It operates without restriction on the policy space. It works by reducing the complexity of CBCR to standard contextual bandits, and it can work with any contextual bandit algorithm, not just LinuCB that I presented in the paper. And so this can have several applications in recommender systems, including fairness problems. And what I didn't present here is that other advantage is that it works for generic reward functions, not just linear rewards, and it works for smooth and non-smooth objectives. And that's important because in multi-objective problems and in fairness, there are objectives which are non-smooth. But limitation of this setting is that it doesn't account for many aspects of the dynamics of the recommender systems, such as problems where there are feedback loops because the recommender system has an impact on the user behavior and preferences. And also the fact that recommender systems are highly dynamic because the item set is never fixed. And also in the real world, recommender systems are part of very complex pipelines, which are typically made of multiple stages. And so this is just like a very simple model of what a real recommender system looks like. But we hope that it's still an interesting setting to study, since contextual bandits are still a popular tool to model recommendation these days. So thanks for listening, and I will be taking questions.
Yeah, thank you so much for your talk. I open the floor to anyone who has questions. Please feel free to ask.